We have decided to do our presentation on quantum cryptography and the different kinds that could help when quantum computers become a realization in our world. So the first one that we'll look at is lattice-based cryptography. So a lattice is basically just a repeating set of dots in some kind of plane. It could be multiple dimensions. So these are two examples of two-dimensional lattices. So as you can see, they kind of make these ever-going, forever sets of dotted planes. And the lattice-based cryptography uses these things called bases, which are two vectors that will span the entirety of the lattice. So if you look at this first picture, B1 and B2 are two vectors that span the entire plane, and what that means is that there's a combination for B1 and B2, some kind of combination that will be able to span and reach every single dot in this entire plane. And the idea behind lattice-based cryptography is using these basis vectors to get to certain points on in this lattice and finding these combinations to get to those points that represent a letter or a word or whatever it may be, a symbol, and the problems that can arise and how difficult it can be when you have these basis vectors. So why are lattices a good idea for quantum cryptography, and why is that such an emphasis? Well, first, there's a lot of understanding and analysis that's been done on them. People have been looking at lattices for a really, really long time. So we have a good idea about what uses they have. They're very versatile. So this idea of lattice-based cryptography has so many like it can go into so many different fields where security is at at hand. It's super popular, similar to the first point that there's just a lot of work going into it, and we have a lot of information about it. And mainly the most important part of this is it's very difficult and like worst case hard. So this worst case hard idea is the average problem for a lattice, like a lattice problem, is very, very difficult as opposed to factoring problems, which are average case hard, where your average case is like somewhat difficult because you're always going to have, no matter in what field you are, but you're going to have super hard problems and you're going to have really easy problems. In lattices, your really hard problems, there's so many more of them that make up the total amount of the problem. So it means that breaking lattices is going to be very, very difficult for people to do. So the application is as such. So imagine we have two sets of basis vectors for this lattice, just a simple two-dimensional lattice. And the first basis would just be S and V. So that basis is called a good basis because it's very easy to understand. And so if we wanted to get to, say, this point here, we could just do 1 times V negative S. So it'd be 1V negative 1S, and that would get you to this point. But now if you ask that same question with these two vectors, B1 and B2, they also span this entire lattice, but it's a much more difficult question to get to this point. And the bigger point for lattice-based cryptography is one person will decide, hey, I want to get to T because T is in this lattice, but I'm going to say that the point is Z, which is slightly off from the lattice. And they would send this, and you have to find the closest point to Z because Z isn't a point in the lattice. We have to find the closest point to Z. And this idea of finding the closest point in lattices is an incredibly difficult computational method. especially because these lattices can go forever and ever and ever. And especially when you get into multiple dimensions where this is just a two-dimensional lattice. But if you get into thousands of dimensions of lattices, it can be really difficult with multiple of these basis vectors, where if it's a 10-dimensional lattice, you have to have 10 basis vectors. Or if it's a 10,000 dimensional lattice, you have to have 10,000 basis vectors. So when you get on this massive scale, one, you get all these different kinds of points that you can have, so you can represent almost anything that you can imagine, and it becomes incredibly difficult to break because there are just so many different combinations. It's so difficult to figure out what is actually the best combination for these vectors to get as close as possible to the point that you're looking at. So that's the application and how it would work is that you just use these easy vectors to pick a point, and then you have these not easy vectors or these hard bases in the actual message. Our next type of cryptography is hash-based cryptography. Hash-based is being utilized right now as well. So what hash-based is that you can take any text and put it in what's called a hash function, and it'll give you a hash value. This text can be as long as the longest book, or it can be a single word, and it'll still give you a hash value that looks similar to this. And this is really useful because it just completely not encrypts, but it represents this text in a very unique way. So why is hash important? So the biggest reason is it's one way. It's almost impossible to break. Uh, it, you only have one way of going through it. The hash doesn't, it's not like some kind of code. It doesn't represent any of the text or the data's. It doesn't have some kind of sequence that it does to do it. It just spits out this hash representation, and it's irreversible. It's almost entirely unique. So they're very, very low probability that you're going to get the exact same hash for different kinds of texts. Those, when you do have the same hash, is called a collision, and it almost never happens. Very, very rare. Another benefit is it's super, super fast. You can just put your text into a hash function, and almost immediately you can get a hash from it. And then the biggest thing is it detects changes. So if you put a text into a hash function, say it's a big book, 1,000, 2,000 word page book, and you put it into a hash function, if you change one singular letter or one singular punctuation in that book and put it in again, you get a completely different hash. So this is where hash can be really useful in quantum cryptography because it'll help detect changes in when people like log into or when people try to uh, mess with and change or alter some kind of document, which means that they've been there and they've made changes. Hash is going to be able to detect that. So the big application for this is passwords. So this is where it's used right now as well. So a lot of company or websites, they they don't actually save your password. They save a hash of your password so that the next time that you come into the website and you enter your password, they compare the hash of that to the hash that they had saved. So this way, if a hacker or somebody does get onto that website, all they can see, they don't see your passwords, they just see the hash of the passwords, and there's no way that they can actually get those passwords because it's just a hash. Hashes are irreversible, you can't figure it out. The other application here is the blockchain, which the blockchain is going through a series of different blocks to keep things secure. So what the hash will do is you start at one block and then which is some with some kind of data, and then you go to the next block but you save the first block as a hash, the first block as a hash. And then you use that hash in the next block as well. And then it's just a continuing snowball effect of that. So this is really helpful to see if people make changes or hack onto one of the blocks, it'll change the how your blockchain, it'll be really easy to see because these hashes will be completely different. Um, this is really helpful for security because it's really easy to catch the mistakes and catch where hackers might come on and try to get some kind of information. Like you can see it very easily by just looking at the hashes, and it's really easy to like have alert systems in place for that.
The last system that we will be looking at in post-quantum cryptography is code-based cryptography. Now, code-based cryptography is heavily based on the idea of code errors and checksum algorithms. Now, in code-based cryptography, we will take our original message, our plain text, and we will intentionally introduce errors into the message through some code error algorithm. And we will get our encrypted text or our ciphertext back that we can send to whoever we are sending our message to. Now, on the other side of that, our recipient will have some sort of checksum algorithm that will be able to undo the errors we have intentionally introduced into the message, and they will be able to get back the original message. Now, this system has been thought of a lot in post-quantum cryptography because it is not factoring based. It uses some modular arithmetic, and it uses a lot of math. However, these systems are not heavily reliant on large numbers that computers these days cannot factor easily. This system is fast, especially in its encryption and decryption, even though it has been heavily looked over because some of its keys are really, really large and can be up to as a couple megabytes large. There are currently no known attacks for some code-based systems, which means things like Shor's algorithm that could easily use quantum computers to factor large numbers and break systems like RSA will not be much better at cracking code-based systems, which gives it a sort of edge over current systems in keeping our data quantum safe. Some applications, McLeese's algorithm is probably the biggest application of code-based cryptography. It has originally been looked over because of its large keys and because there wasn't really a need for quantum safe cryptography at the time. However, it has been heavily scrutinized now and is currently under research as a pretty good candidate for post-quantum cryptography over the internet. Now, McLeese's algorithm uses GAPA codes, which are checksum algorithms. Basically, they go through bits of code and use heavily sophisticated mathematics to check and correct any errors that there may be in the code. So using McLeese's algorithm, Alice, for example, could intentionally introduce lots of errors into her message, send it to Bob, and Bob could use GAPA codes re to decrypt her message, and he would have the original message. Now, these are pretty safe from intermediaries because of the fact that since you to decrypt the message, you really have to understand how Alice introduced errors into her message. And if you don't know how Alice introduced errors, there are billions of possibilities for what the original message could have been. And it is very, very difficult to figure out the original message from that. Thank you very much.